Okay, fine. We got now. Okay.
Okay, sir. Now it's fine. So can we start,
okay,
sir?
Just 1 minute. Just I will request my student volunteer to introduce you to the audience. Monica, please introduce Dr. K. Venkat Reddy to the participants.
Sure, sure, sir. Thank you. Good afternoon, one and all. I'm pleased and honored to introduce our guest, Dr. K.V.Reddy Garu, Associate Professor at NIT Warangal. His research works, contributions, experiences are a representation of his hard work and dedication. He did hydraulics and water resources engineering at KREC NITK, Suratkal 2002. I feel elated to say this. And then he got his PhD degree for distributed rainfall runoff modeling of watershed using fine. On river basins of USA. Climate change impact studies on river basins of USA using climate models. From July 17, 2013 to Jan 17, 2014. His hard work was recognized in the form of awards. He has received many awards such as Young Engineering Research Award 2016 for the research work carried at NIT Warangal, presented by NITW and NITWAA 2016. Raman Fellowship for carrying out postdoctoral research work at Texas A&M University, USA under Indo-US 21st Century Knowledge Initiative for 6 months from July 2013 to January 2014 by Government of India in May 2013. He was selected for teaching staff mobility under ERASMUS scheme into University of Santiago de Compostela, Lugo, Spain for 1 week and gave 8 hours of lectures at USD Lugo. Best Paper Award for paper entitled Object-Based and Knowledge-Based Classification Technique in Urban Areas using Hyperspectral Imagery and LIDAR data for my graduate student in nationals recent advances in remote sensing and GIS with special emphasis on mountain ecosystems. He bagged first rank in 2002 REC Suratkal, Mangalore University. Apart from all the degrees and rewards, his research projects display his passion. His research projects include development of rural information system using high-resolution satellite data, GIS and GPS, development of precise and real-time simulation watershed modeling system using advanced geospatial and soft computing methods, development of 3D spatial information for NIT campus, estimation of government water recharge using advanced geospatial and soft computing, a decision support system for climate change adaptation of chain task systems of semi-arid region, short and medium range flood forecasting system for Godavari River Basin, using ensemble weather forecast. Power is gained by sharing knowledge. I reminisced this quote while learning about him. He had contributed 37 journal papers, 72 conference papers, on numerical climate prediction 18th to 29th June 2018. In higher education. CEP on art programming concepts and applications for teachers in CEP on advanced mapping techniques for planning and management of resources under TechCube 3 during 21st to 25th May 2012. Open source software for civil engineering applications and applications of SWAT model in water resources management on 30th December 2014. Besides all this, he has been serving as course coordinator MTech RS and GIS from 14/7/2017 till date, coordinator for Center for Advanced Geospatial Solutions and lab in charge of RS and GIS lab from 1st July 2008 to till date. So glad to have you here in this virtual session, sir. Thank you so much.
Thank you, Monica. Now, Venkat Reddy garu, now you can start your session.
Yeah. Thank you, Monica, for the nice introduction.
Thank you, sir.
So I will proceed with the presentation.
Yes,
The
sir.
previous speaker is explaining about some of the QGIS software, how we can work. Now I will I will explain some of the, you can say, applications where you can use this geospatial techniques like GIS, remote sensing, in the especially in the field of water resources, specific to watershed modeling and management. So those things I will explain with some of the case studies where we are working.
वो खत्म हो गई नहीं लगाऊं क्या
So you see the, you can see first of all the, you can say what is the watershed and how that watershed modeling and management can be done, and what are the geospatial techniques which we are discussing, and how these geospatial plans are useful for watershed modeling. Then we can see some case studies where we can apply this various, you can say, this different, we can say, geospatial methods for understanding the watershed process. Those things we'll discuss one by one. As most of you know who are there, actually, is watershed is nothing but an area that drains the surface water to a common outlet. So it is the, you can say, basic scientific unit to make lot of, you can say, any of the, you can say, measurement of the hydrological process or understanding of the hydrological process, or otherwise even to planning, management, development, you can do starting from the, you can say, this watershed level. So from watershed level we can develop, so it can go up to the, you can say, different levels. We can extend further, like catchment, basin, like that we can extend. So you can see here what is the, you can say, watershed, and it's you can things. Most of you know by this time what is a watershed. So here you can prepare the, you can say, this watershed is a, you can say, ridge line. This ridge line, and it contains inside the drainage, and in that whatever is the, you can say, flow process, like maybe sediments, maybe water, nutrients, whatever comes inside, they will finally flow to a common outlet. That is the basically the, we can call as the watershed. You can see the, you can say, previously also we are discussing some of the previous class for you, actually, the digital elevation model, which will become the, which will make the, you can say, basis now to whatever we want to model, simulate the hydrological process of a watershed, or even planning the you can say, various you can say, intervention techniques to develop the watershed by using geospatial methods. Most of these things, geospatial things, dam is the main input. So you can start with the dam. So there you can apply the various techniques, and you can understand the, you can say, process. So the dam, same dam, if you see in the 3D modeling, so 3D model, it will look like something like this. This is our, you can say, now today what are the, I am explaining, going to explain next, you can say 1 hour. This is the basic thing. So where we have the, you can say, the digital elevation model in 3D view, and you see that this is the basic drainage. It will take to the, you can say, overall, you can say, basin to a one outlet. So this overall, the, you can say, the occurring of the rainfall, then occurring the later, especially once it is appearing as a rainfall, then how it will finally appear as a runoff at the outlet. So it involves so many process. So we need to understand those process. Along with that thing, it will not only carry the water, it will also carry sediments, nutrients. So many things, and these are like influenced with the various changes which are like changes which are occurring in the land use land cover changes, and even the climatic changes. So many things will influence the how the process will work in this watershed. That is our basic is understanding point. So if you see the, you can say here, what are the previous shown. So now we keep in the form of a flow chart, like what exactly we want to, we can say, understand in a watershed. Okay, so it's like a basically the precipitation is there, that is like it is coming as input. Then it will come into the land surface. Now there is like a different process we can expect. That is like a one is evaporation, it may takes place, evaporation, evapotranspiration, it may takes place. Then once appearing as the land surface, now so it will split into the, you can say, as overland flow, and some part will go as infiltration. From infiltration, once again, some part will come as interflow to the stream. Okay, after going something as a groundwater, still something will come as a base flow. But everything finally come to a, you can say, a stream that will flow basically to a higher order streams, and then finally flows to the, you can say, stream outlet, or further you can say bigger, you can say, river or river. Here, yes, what are the various watershed modeling aspects which you are really interested, which you can normally do in the, you can say, by using the geospatial methods. So normally watershed modeling, one of the things basically we look at the what are the various hydrological processes which are working, and how we can simulate or understand, or you can say analyze them, or you can say process them, or you model them, or you can say predict them. That's one of the main important thing in the watershed modeling. So other one is like a, of course, the availability of the, you can say, water for the present conditions and future conditions. That is called prediction of the water resources. It's one of the core of the, you can say, watershed modeling. Then something like a climate change impacts, how the, you can say, really climate change will impact the watershed process, that can be studied. And qualitative issues, I said, like a, it's water not only carrying the water, it will also carry the sediments because of the soil erosion. It will also nutrients because of the lot of use of fertilizers and pesticides. So they will all like a, you can say, add the various quality related issues to the, you can say, water. So all things can be also be studied as a part of watershed modeling. So here, when come to management, so it's like watershed modeling and management. Now, management means we have to see the understanding the various process. Suppose if we do, then how to, suppose you want to improve the quality. Suppose you want to stop the water in between the watershed, so that it will be water available for some various agricultural practices. There all comes under the management, you can say, practices which you can perform over the watershed. That's how you can say one of the, you can say, area where we can use the geospatial techniques or methods. Of course, that watershed development is that process where we can do a lot of interventions so that we can improve the, you can say, maybe vegetation or maybe the availability of the water, so that it will create finally at the end, it will add to the, you can say, livelihood to the people who are, you can say, residing or who are at the, in the watersheds. Okay, so we can also develop the different decision support systems, like how to best use of the available water resources. Okay, how we can allocate for the different, we can say, stakeholders. So all things we can perform as a part of management. Also we can do the real-time monitoring. Now with the current, we can say, available technologies, we can real-time monitor how the things are happening in the watershed. When the, you can say, water, of course, once it is appearing as a runoff, how it is flows, how much sediments it is carrying, everything. Nowadays we can do a real-time monitor. We can real-time we can monitor those processes. So here, as we said, like a geospatial methods, I think you are today you are, you can say, morning you attend some classes, in the afternoon, and then rest class also. What are the basic process? So one of the two important process, the one is like a geographical information system. That's what is the, just now you got, you can say, some introduction, like how you can work with the QGIS. Then the remote sensing, where how to get the satellite data or any, you can say, image data, and how we can use for the various, you can say, understanding the various you can say, real world features. Then there are other two things are there which are not so prominent which can come to the watershed, but still we can use whenever they required. I'll say one is photogrammetry. Somebody also, like a priest asking, like how we can make a dam. So one of the method is like we can use the photogrammetric techniques and we can develop the digital elevation model. Dam, that's one of the most of the data which you are presenting right now in our websites. They're all like a developed one. Some of the things are by the photogrammetric techniques. Okay, so then of course the global navigation systems is one of the, you can say, geospatial method where we can get the, you can say, real-time location of the, you can say, location of the objects or location of the places, but also like important for some of the things to understand. Okay, so then question comes, okay, watershed modeling is done like a, you can say, so many years back. Now geospatial methods are getting slowly prominent, you can say. Of course last week maybe the, you can say, 10 or 15 or 20 years but previously also watershed modeling is there. What else we can do with this? We can say geospatial methods. So here the way the previously the watershed modeling is done and the way they done, now we can do in a better way, or we can do the better modeling, simulation, analysis, prediction, all things we can improve to an extent. Since we have now we have the, you can say, any type of resolution data is available, we have any type of the temporal data is available, spatial data is available, so we can make it like a really, we can improve the understanding of the hydrological process in the watersheds. You can do a lot, and you can really make a better, you can say, prediction of the, you can say, hydrological process when compared to previous, you can say, type of, you can say, working types or methods. So here applications of geospatial methods in the watershed, you can say, modeling and management. So really, yes, when come to the, you can say, these geospatial methods, where we can apply this this geospatial methods and where they will really give the advantage in the watershed modeling. Okay, first of all, the main thing is they will provide this all the geospatial methods, or you can say techniques. They provide a very good, you can say, distributed data or high resolution data to the, you can say, watershed modeling environment. So there you can say watershed modeling, it involves a lot of, you can say, data. That all things we can provide through the, you can say, this geospatial methods. Okay, so we can integrate with the, you can say, now GIS, like just now is on QGIS or ArcGIS or any softwares, we can quickly integrate with the other, you can say, the environmental data which are available, maybe some other, you can say, database format. We have this geospatial data format, so we can integrate and directly we can connect to the watershed models. Okay, so we can directly model in the, you can say, software itself, or you can take the develop the required things for you, like inputs, some initial things. Then you can go to the, you can say, model, you do the process, come back to once again to GIS once the model is run with the outputs, and you can visualize. So we can visualize the output in different formats like a 2D format, 3D, 4D, animations, any of those things we can perform. That's what is the, you can say, we can do with the, you can say, geospatial, you can say, methods. So here, what are the different application areas of the, you can say, geospatial methods in a watershed, you can say, modeling and management. So we can have the, you can see, you see that plenty of the things which we can do. We can map and monitor the, you can say, surface water bodies which are there in the watersheds. We can map the groundwater potential zones, rechargeable zones. We can use basically more intensively for watershed management, command area management, and like this we see the plenty of applications which you can perform. Okay, we are using the, you can say, geospatial methods. They are like improve your understanding capability, or you can say analyzing capability, or you can say visualizing capability. So this geospatial based models, you can see here we have the, you can say, plenty of, you can say, models which are available, or you can develop your own modeling concept, or you can methodology you can develop and you can work. So the main thing is here we have the, you can say, SWAT model, HMS, HGOHMS, across. So this is something like if you want really want somebody asking press like some flood modeling, so we can do with the across, HGOHMS. You can want something like a quality related issues, you can do with the AGNPS model, EPONET. Okay, for suppose water distribution network, something you want to make. There are some other things which you can really use in the, you can say, you can build the geospatial data and you can use in the watershed modeling and management. Okay, some of the databases which are really useful for you to work with the, you can say, your modeling and you can get these are the, they become the basic sources for you, data sources. So from these you can develop, you can apply to any of the, you can say, your, you can say, models. Okay, so you can nowadays like a somebody asking like a previous question now, like we can how we can prepare from core like a topo sheet, and then like a different data sets like a watershed boundaries and so many things. So now here there are some plenty of options are available for us. You can use these data sets like a B.V.N, USGS, Industrial Geological Survey, SRTM, ASTER, there are the dams, FAO. You can get a lot of land use, land cover, soil information. Most of your databases nowadays are available on the different, you can say, web sources you can use. So some of the examples, how we are using also I gave in the coming slides. You can check really, and you can also, whenever you want, you can always try these things, and then you see how you can really use these data sets. Okay, so now yes, I gave the, you can say, brief, we can say connecting things like how watershed modeling we can do, and what are the applications we can make, what are the geospatial techniques we can make. Now, so I will explain the various case studies which we are performing at different, you can say, times. So on the, you can say, how we can use these geospatial methods to understand the water resources, water related, you can say, aspects, especially watershed related process, and how we can able to understand, and how we can able to perform, and all the things I will explain case by case. So I am presenting the three types of case studies. Like a first one is like a modeling of the watershed process. Second one is management in the watershed, how we can manage a developed watershed. Like a, there are some, we can suppose some watershed intervention they did, suppose some NGOs or some government, how to understand that whether that is like really giving benefits or not. The third one is like suppose some climate change, you can say, studies are there, how really we can make a climate change study in a watershed. Those are the, you can say, case studies which I am going to explain further.
Thank you everyone.
So here, this is the, I can say, just like I am providing the, I can say, basic framework for the watershed model development. So here, this is the, I can say, we developed as a part of the, you can say, work here, doctoral research work. So here, so how to, you can say, use the, you can say, developing the hydrological model by using the geospatial data, and then how it can apply and how we can visualize the outputs. That's what is the, you can say, concept here. So here all like preparing the, you can say, the model available models and preparing the data sets and integrating the things. Then finally we can say evaluate the, you can say, model which we are, whether it is working fine or not. That's the thing. So in all those cases you can see we are almost like using the geospatial data, you can say, as a one of the prominent sources, so that we can do whatever the checks, whatever we can say, you know, what are the process we are there, or to check how much we can improve the hydrological process. So all things we can check with the geospatial methods. Okay, you can see the, you can say, basic, you can say, the watershed, you can say, process. You can see in a particular watershed how these things are there. So why these things are required is each one is a one process. Rainfall is occurring, then that will flow to the, you can say, as a overland flow. Then some part will go infiltration, something as interflow, and some basically appear a channel flow. Okay, so each other things we need to understand in a geospatial system, that how we can model them, how we can give input to the, you can say, hydrological model, so that model equations we can use and we can simulate. So this is the, you can say, thing. This is for this we need to understand the, you can say, watershed, how it look like, and how you can really model the, you can say, process. Here you see the, you can see, this is the, you can say, real watershed actually. So here we need to model them now. So what we do is we can, you can say, we need to make a best geometrical shapes, so that we can use the basic equations of the watershed models, and we can able to simulate this, you can say, hydrological process. So here you see the, you can say, the some of the strips, rectangular strips. So this is the real, you can say, things. So we need to, you can say, best approximation we have to make, and we need to analyze the, you can say, this flows. And if you take one of the strip is looking something like this, and in that one thing, if you want to, this is the way it will look like. This is the way it analyze it, prepare the, you can say, watershed, you can say, grid representation. Similarly, when come to channels, so this is the channel, and each, you can say, channel, it look like something. And if you take a particular one part, it look like a trapezoidal channel of this thing. So one element. This is the way that it is like, first of all, conceptualize the complete watershed, how it has to be modeled in a geospatial things, and how we have to take it to the is a watershed modeling system program. Okay, so here I think most of you, some of you may be already aware of this water resource aspects, how they are made a fundamental, you can see, simulations of the runoff. There are so many basic equations are there. So there is a something called a kinematic wave equation, and GAML, that is called infiltration models. And these are the different type of the, you can say, models which we considered to understand the from rainfall how much runoff will come. That's what is the, you can say, understand. So in between, like a whole the process, how we can able to formulate, how we can simulate, and how we can understand those process. Okay, so here, so this is like a different things, whether to consider some of the aspects or not to consider accordingly. These things are there. So here, same thing, once after making the complete detailed model, then applying to the different watersheds which are available across the, you can say, world. Some in the, you can say, within the country more, and then other things also checked, and then whether we are doing correct or not, all things are got, we can say we are verified actually. So the different watersheds checked actually. So here, this is the, you can say, different, you can say, watersheds which are at the different parts of the India available, and this is like one of the watershed which is available in the Netherlands. So these are all like we need to have the something called, you can say, some observed data that these things are, we can say, selected. Similarly, the summer watershed in the, you can say, United States. So these things are selected. So these things are like used to, you can say, to verify the, you can say, developed model, which is like actually the part of my doctoral research work. So this is the model is developed and verified on this different basins. Okay, so here just we can see some of the, you can say, example like how we took the watershed and how we prepared the database in a geospatial environment, and how taken to the, you can say, model and how we applied. That's all like a things which I'm going to explain. Yeah, the basic information about the watershed, how the watershed is there, what type of soils are there, and this is one of the study, you can say, project watershed taken under the, you can say, Indo-German project. So they collected this data, means this is the, you can say, they developed, and they, so we inquired and accordingly we got this data to apply to select. Since right now whatever I am showing is a event based model. Event means whenever there is a rainfall event occur, so we will immediately simulate that rainfall event, and we will come to know when the peak will come and when the peak time will come, and what is the overall volume of the, you can say, runoff will come per particular event. That's what is the, you can say, aim. So that's what is the, you can say, study here did. This is the, you can say, different, you can say, data sets actually. So we use the ArcGIS. So here prepared the, you can say, first of all land use land cover maps. So from remote distance data we can prepare the land use land cover maps. From land use land cover maps, basically for hydrological models, we require the Manning roughness. So the Manning roughness is an influential factor, like how much runoff will takes place. That's all you can say given in the, you can say, thing. So where so we, because this is all like I did in the part of a JS only. So where we need to prepare the land use land cover map. From land use land cover we need to prepare the Manning roughness map. Okay, similarly we need to make something called finite element grid map. This is to, we can say, core of the hydrological model or watershed model, where how we can take the simulation we can do. So that all things also we do the JS, then that all things inputs will export to the model. You can say the original, you can say the how the watershed, you can say the a stream look like in the, you can say, watershed. This is the, you can say, the once we prepare in the, you can say, geospatial environment, this is the way the overall, you see, this is the outlet point and this is the overall drainage. This is the somewhere the photograph should be somewhere, this is the point location. This is the digital elevation model. So at that time when I prepared, this is prepared from the, basically starting from the fundamental principles of you can say contours from them. But nowadays we have so many data sets are available like SRTM. So all things we can download and we can clip for the watershed, you can say the boundary, or you can ask system, it will develop the complete boundary and you can use that one. Okay, most of the models presently using SWAT and other models, we can develop your own, you can say, boundary. Once you know the distillation model and you know the outlet, remaining all system will take care. This is the, you can say, overall, you can say terrain, how the terrain is look like, and then this is the, you can say, the dam, and this is the way the terrain, whole terrain of the particular area look like. This is the, you can say, the this satellite image, false color composite map, it's the IR satellite data. So based on that, prepared the, you can say, land cover map. This area like basically three things. One is like a forested area, agricultural land, of course the remaining is the wasteland, or you can say barren land. The agricultural lands in the watershed which are available, and of course this is the, like how the stream look like in the, you can say, basin, particular study area. This is the overall, you can say, the dividing the whole watershed into the, you can say, different elements, and you can say different elemental data sets. So this is the background blue color, whatever you see the original streams, and whatever you see the foreground is the network, channel network or the prepared network, which is this is the different, we can see the all the information about how this is done actually. So this is like a different, we can say, events. You see, this is some of the events which are, you can say, tried or checked for the, you can things which are available in the literature. Now, this is like a at the project's time they collected this all the data sets. Those data sets only be taken and to study the, you can say, things. Some of the parameters we need to make it for the hydrological model. So when you are simulating, we need to adjust in the calibration phase. We need to give as input these parameters based on the fundamental, especially initial field verification. We will take some of these values. Later we need to improve or change a little bit depending upon the you can say model calibration. You see now these are the, you can say, the black one is the, you can say, observed one, and this is the blue one is the, you can say, simulated one. You see, this is the way the simulation takes place at the end. Once the whole inputs we are giving and after doing this simulation, it's like a this is simple, you can say, events. It's like an event based model actually. This is the second event, third and then fourth. This is the way we can get how the, this is all like a developed model, how it is really behaving with the, you can say, data sets or you can say model or inputs, different inputs, how it is giving the output. So some other events like a validated events, these are all. Calibration means where we will adjust the parameters. In validation, you will not adjust the parameters, you will directly use those parameters and you will simulate the process. These are some of the, you can say, things. So you can see the, you can say, different, you can say the how much you are getting observed and simulated difference, and how much you are getting the peak runoff difference, and what is the time, but time per peak. They are like very much useful for the, you can say, for, you can say, when you are working with some flood modeling or flood simulation. These are very important. Okay, so we need to know all these things and we can work on these various aspects. Okay. Similarly, this is like a one Indian watershed. Similarly, we did for the, so one we can say yes, watershed, the same thing. So same way the overall concept is same to how to apply preparing the data sets. Okay. So the one thing I want to say here is this is like a rainfall map, gridded rainfall map. Okay. This also like a, you see nowadays the rainfall also available as a gridded map. But in the, you can say we can use in the GIS softwares. We can develop like this and we can give input to the this rainfall also to the model as a point observation, or we can give as a this one, so that we can do in a better, we can say, the simulation of the hydrological process. You can say the grid, different ways of doing gridding. So regular gridding and you can say networking. So this is all like I will know how we can do the simulation of these things. I want to tell you one thing is here most of the things are everything is done in the, you can say, geospatial environment. Modeling is done in a, you can say, model, which is like a developed one. So here are the different, you can say, events which are simulated events with a different type of the, you can say, networks, and the simple, these things are all given here. So here we will have the, you can say, here even for the, you can say, the this watershed, how the, you can say, we can have the, you can say, different, you can say, with network, without network, what is the observed one. So all things also given. So these are the, I can say, things like whether we consider a single network, channel network, or single channel. These are all things observations. So how we can get the, you can say, different, we can say, for different simulations. What are the variations we will get? All the things we can see here. Okay. So even we check the sensitivity analysis. Means here most of the modeling, especially the watershed modeling, some parameters are very sensitive. Means they will influence most of the hydrological process. For example, you take the hydraulical conductivity. It's like very one of the very influential parameter. Similarly, the initial water content. You see, so in a watershed, there is a initially lot of, you can say, moisture is already there. It is easily will get the, you can say, the remaining water available as a flood. Okay, so that will all like a overall complete process is influenced by the how much is water available initially. So like that. So similarly, the manning roughness, they are like a channel manning roughness. They are all like influence the when the peak will come, how much peak will come. All some of the times you can see these parameters will all you can say influence. So we need to check the, you can say, the influence of these things. So we need to change the, you can say, different parameters, and we can verify yes how much we can really change these parameters and how much you can really it will, you can say, improve the, you can say, parameter range. So all things you can understand, or you can say study. So with this all like even some using the different grid size, how it really will influence the process, even changing the time step. So here we use the 30 minutes time step. So what is the 50-minute time step, 60-minute time step, how the things will change, all things also given. These are the some of the things like understanding the things like how the you can say which one is influencing more. So it's like some of the saturated water content, initial water content. These are some of the you can say model variables, how they really influence the you can say flow. You can say the various you can say parameters. Basically the hydrologic process, how this you can say the parameters will influence. This is the you can say different grids. These are also once again prepared in the GIS. You see, suppose you use the boundary grids at the you can say you see instead of using single you can say things, so you can make a like this type of radial strips. How it will influence that also like we tried and verified. This is like using, so that's all we can see some things. Of course, what is our case is like we didn't since the way the division is done and then finally added, so it is not a much change is not there. But this is like all check for us how your real network, all things will really influence your complete you can say process. So this is the you can say things how the you can say the we change the grid, we change the parameters, how much is the change is there in the different you can say things. Okay, so in the volume of runoff, peak runoff, time to peak runoff. So these are all very important for you now. So peak runoff, time to peak runoff is very important, especially in the flood thing now. So they will influence you can say our you can say results. So that all we need to know how much you are really changing the grid may change your you can say overall simulation process. Okay, similarly with the even time step also, how the really time step will change or influence your process. Some even the we can make some we can statistical evaluation also like a completely how it is close, or you can say the what are the values between the observed and then this what are the similarities coming close or not. This some of the you can say maps. So as we observed, most of things are coming close, volume of runoff, peak, time to peak, which are very important parameters. Okay. And finally, this I want to tell you here. Yes, this is like a once we made a complete we can say model. Okay, so here this thing is the you can say once after getting the you can say the input, we have to prepare in the GIS environment where the model will simulate those things. Once after getting the output also you can the outputs we can bring back to GIS and we can visualize. So basically the simulation you are getting, you will get at the only outlet now. But what about the changes which are occurring within the watershed? That is like a GIS, either you use QGIS or ArcGIS or any other software. It's like one of the best thing for us. Now we can bring back all the intermediate outputs, is the grid level outputs, and we can visualize the how really the it will you can say the flow takes place in the watershed. This is very much important or useful in the flood simulation studies or some hydrological process studies. So all cases is very much important or useful actually. In this case, so like every like what we did is like of course we can do animation. In this case we did like every 10 minutes. What these are all like different grid points. These are all like different grid points. So you see the overland flow, which is like you see the different color here. This is the different colors, which is at the starting of the 10 minutes time. And you see channel. This is the channel here, but there is no much flow here in the initial times, and there is a lot of flow. You see higher values red color at the in the you can say watershed. Okay, so term 30 minutes. So you see most of this become the you can say blue at the you can say ridges. This is there. Here the channel is there, and this is like a one side water will flow, this side water flow this side. So you see here the initially the high flows are coming to the middle portion, and the end portion are getting like slowly water is this is like single event thing. Okay, so now channel is making easily you see here and come to 10-60 minutes. Most of the water is coming near to the you can say middle of the watershed. And you see the you can say when at 100 minutes you see no water is available in the thing, you see the complete you can say you see 0 most of the things, nothing is available in the watershed. You see the here we are getting a bright now, that is like a channel where the water is there. You see the water is there here red color now. See the place the where channel water is there. Okay, this type of we can say the analysis, even we can same thing we can make like an animation, and we can see how the really the overall flow when starting of the rainfall event how it is looking like, and at the end how it is looking like, all the things you can always verify. This is one of the very important useful thing in the GIS. So somebody really want to explore the full potential of GIS, so they can really water resources application. We can see whatever the output comes, you can bring back to the GIS environment and see how that particular simulations are there. So here, with that previous concept, which is like a developed as a doctoral, you can say research work. Then later, so I gave some of my, you can say, scholars to further work on the how to develop a real-time flow simulation model. Since now we have the, you can suppose there is a complete network of sensors are there available in the watershed. So complete processes are available. So can you bring everything into the computer and where we can do the real-time simulation of the, you can say, process. So we can monitor as when how much the flood is coming, water is coming, all things. That's what is the thing. This is the what we got the even fund from the Department of Science and Technology also to work on this thing and then further to develop. So this is the, I can say, experimental watershed we selected here to Warangal, and then where so we gave the even did lot of, we can say, some of the instruments also we kept. This is the, you can say, the watershed where these are the different, we can say, input, we can say, geospatial data sets for the watershed. Okay. So we can say planned, you can say, some of the, you can say, digital water level recorder and automatic weather station in the watershed. So some of the instruments we prepared and then installed here in the watershed. These are all like data sets. Initial our plan is to get everything in the, you can say, get back at the, you can say, institute, so that we can able to use that data and then we can make. So these are the, some of the things. These are like a digital water level recorder in the stream, like where we can do the measurement. These are all in plan is, these are all like will come as a, we can say, available at the, you can say, institute through the, you can say, the tele, you can say, metry, and then those things we can use in the watershed for the simulation. So we can do the things. But these are all like instruments we did and some initial things we did, but later because of the, you can say, one is like a, the monitoring is getting very difficult at the, you can say, at the, it's like a faraway place, almost 50 kilometers away from the things. And later it is like some floods came initially, they all like instrumentation got damaged. The later it is getting like a 1 year completely, there is no water available. So in that way we could not do much, but the initial idea we made and then lot of initial work we did, background work. We are in the process of, we can say, developing a full, we can say, real-time model with these things by using the other sensing things also. That's like that work is under, you can say, progress. Then the next one is the, you can say, one of the, you can say, our, you can say, MTech students worked on the how we can, say, prepare the, you can say, this. Suppose most of the things you can see in the, you can say, rural areas are there developing the watersheds. Development means so constructing the various type of, you can say, intervention things. Means nothing but constructing some check dams, nala bunds, improving the vegetation, forest growth, which all will improve the vegetation and water source in the watershed, and they are all like a indirectly will help the, you can say, give the livelihood to the people who are available there. Okay, so in that so we checked like a one of the watershed which is like already implemented some development activities, how real it is giving the, you can say, benefits, whether it is like a, how much benefit we can see, it all we can really do with the remote sensing and geospatial methods. So any concept where we want to check pre and post of that development activity, our remote sensing techniques are very much useful. We can do at, we can say, at most, we can say, accuracy, and then with, you can say, complete detail, you can check, so you can develop and you can prepare. Only thing is we need to have the prior and after giving benefits or not. Hello.
Hello.
There is some problem in the, I think, presentation sharing. I think presentation is visible for you. I think there is some problem.
No, I'm seeing one slide, impact of watershed development activities.
It's coming now.
Not yet. Yeah, now we got it.
Yeah. So we took some of the you can say cases like where the you can say this study like very near close by the you can say different watersheds which NGOs they are you can say applying the you can say techniques to you can say to improve the watershed you can say this is called like a providing various you can say interventions in the watershed so that it will improve the vegetation and water resources in the watershed. So we took the you can say different watersheds and we applied the you can say technique like how we can really verify this one. Different you can say the watersheds and what is their location and area. So these are the I can somebody is asking like a data sets. These are some of the I can say best sources. Most of your data sets you can get from these websites. Okay, so nowadays you can say you can develop from the field some things which are available for you, remaining which are not available for you. You can always you can say download from the you can say these sources. Most of the things are available nowadays. These data sets. So here we will add the you can say the data sets we can prepare and we can study and we can also like they made you can say different we can say activities in the watershed to develop the you can things. So what are those things like somebody want to see those things or somebody later what is there which are not there and what is there in a letter they made. So all things we can do geotagging. So nowadays it's very easy. So with your mobile also you can go to the you can say field you can geotag the things. That is one of the you can say advantage. So you can see suppose this is like a some of the I can say things which are done in the watershed like a some we can say this is like a Gabian structure where you can some on the Nala they constructed to reduce the soil erosion and to improve the back water and then of course improve the vegetation. So basically to stop the soil erosion and something this is like a small check dam. So this is to you can say make the water to store some time so that it will improve the infiltration and groundwaters in the surrounding areas. So these are all things now like you can very simply background data you can take and you can geotag. So you can use your Google Earth or you can use any of the things and simply you can take photographs and then you can simply your map itself you can geotag these ones. Okay. So here so we prepared now. So you see this like a 2009 and 2014 means 9 there is no you can say this is the okay this is called control area means this is outside of the basin. And this is the you can say area outside these things and this is like inside of the you can say basin. You see the you can say 2019 and 14 you see 19 means like a 9 means before that there is no you can say much you can say you see 9 time and 14 time you see this area how much vegetation is there. Okay, so there is like a vegetation improvement means that is one of the logic we can say we got to take the same month August and you can say same watershed in two different seasons. Why different seasons means one is the time where the lot of we can say rainy season and then other one is the winter season where the you can see initially the so there is some crops will be there and some time and then there is like a two different Kharif and Rabi type it is called actually different showing times also or harvesting times. So that will give us some area information that yes what is the way you are you can say the suppose this is area and you see here control area is outside here inside how much really the you can say area is improving before and after it will give us how much you can really your intervention techniques will help the improve in the your you can say vegetation. So you can compare with the area where the watershed development is not done and the area where the development is done. You can verify like that. Okay, so you can check some of the things like here how the you can say Kharif and then different seasons like a water body and then vegetation cover. So in the different you can say seasons. So control area and you can say the you can say watershed. So how they you can say here they are you can say changing. So between the two things actually here. Okay, so you can this is the you can say some are not I think XY coordinates there's something missing actually here. So there the you can say NDVI like and what is the you can say the land is land cover and then how much is the improvement is there between the you can say before and then after the you can say this you can say control area before and then after doing the watershed you can say or outside of the control area and inside that all the things we can check. So this is the, you can say, case study where you can apply the, you can say, the model for the, you can say, whereas you can say the applications for the, you can say, right now we discussed about the how we can apply for the, you can say, right now the watershed process where we can whether it is improving or not or those things. Previously like a watershed process, how it is improved. So now we can see really how the, you can say, the climate change, you can say the how the climate change studies will, you can say, influence the, you can say the, so we can study how the, you can say, geospatial methods how we can apply in the climate change studies. Okay, so where we can in a given river basin or you can say watershed or catchment, we can also study how the really climate change really influencing the, you can say, the availability of water resources. So I think most of you may know what is meant by climate change. Okay, for a time period in a particular area, the change, you can say, there is a drastic change in the availability of the, you can say, rainfall, or drastic changes in the, you can say, the temperature patterns, humidity patterns, wind patterns. Okay, the availability, the, I guess, occurrence of the monsoon, they're all we can combinedly call as the, you can say, the climate change, you can say, things. So this all like a, if you want to study climate change, so basically you have to use once again the real you can say the benefit of the geospatial methods or remote sensing or GIS will comes into picture in this climate change studies. Since we have to deal with the huge data sets. So climate now, so it's like normally if you want to say one area like weather means the same day things we are discussing. Climate means at least 30 years of data we have to see, and we have to analyze that will help us whether really there is a climate change is there or not. Okay, that you are doing over a river basin. Suppose you take a small watershed, okay, few things will be there. Take a bigger catchment or watershed basin, the number of points will go on increase. So your level of, you can say, difficulty level will go on increase. There are your nowadays the present geospatial methods will help you to understand those things, to work with those things, we can say. Okay, so here just like an example, like how we can apply this, we can say, climate, we can say, change aspect for a given you can say study area. So what we did here, we took the study area in the, you can say, Warangal district. So one of the work carried out by our student. So here completely the what you can say one district took like Warangal district we took. So there are like dividing into, it is an administrative unit now that we can't any hydrological process to understand means we need to have the watersheds. So we divide into number of, we can say, watersheds of basins. In that one of the basin contain the observed data. So that with observed data we all did the calibration validation with the SWAT model, which is once again a integrated model with the GIS, which can able to do the all the hydrological process we can simulate. Okay, so then we can say analyze it for the complete, you can say, district first by understanding a one watershed. Same thing applied for the entire, you can say, the basin or you can say entire district. Okay, so basically we here the things are required, you can say, all the inputs which are like a soils, dam, LULC, slope. These are all very important for this climate models. Similarly, we need to have the present and future climate data. We need to have even the observed climate data. Okay, so these are all things which we make the, you can say, the data we will take in the hydrological model and we can apply. And basically at the end we can ask like what we will study. Means at the end for a given, you can say, change in the rainfall patterns, how much stream flow is changing, whether the stream flow is increasing or decreasing, decreasing or increasing, how much decreasing, how much increasing. That's what exactly we will change the climate change impact. So even we can see like an area like in the part of the basin, suppose very big basin like a Krishna river, Godavari river, like that. Even we will study also like a which part of the basin it is really changing, whether it is like a one small part of the basin it is changing or complete area it is changing. That all things also we can able to study. The area as like a Warangal district we took on, then where we made this, you can say, study. So completely we understood how the really this particular, you can say, concept we can apply. So now it is like, of course, this district itself is divided into 4 districts. When we are studying, it is at the time it is a combined district. So this is the, you see here one of the important thing I want to say here, most of the all the this is like a very rich in the number of, you can say, tanks. So here the lakes are there, also ponds. Here they are called tanks actually. So there are like a prominent. You see most of the this district contains so many tanks. So they are all like a lifeline for the, you can say, agricultural activities in this particular district. Okay, so any change in the climate, for example, happened. So means, for example, for 6 years or 10 years, the water is not coming, means sometimes the tanks may not fill. Then people go on, you can say, agricultural activity they are doing within the tanks, they may disappear, the chance of. So that's why it's very important for this particular semi-arid region to take care of this, you can say, the tanks. So for that, we need to understand the, first of all, any climate change really is there in the this particular area, and how we can influence it there. Accordingly, we can tell something about this tanks, how much water is coming out, things. So here, observed data, you can say, available in the Indian Meteorological Department is taken, and then similarly, even they are providing the climate data also for some of the things like Cortex data. Cortex means is called actually regional climate model data is available. And in our study, we took one climate model and we studied the complete picture. So here, even we can make a number of climate models we can make and we can study, so it will give more clear and big picture about how the climate change is influencing. These are the some of the, you can say, climate points, climate grid points, where the, you can say, this you can see this is the points where climate data is available. Okay, so the triangle ones are the climate points, model points, and grid points are the IMD measuring. You can say the means they measure the complete India, and then they are providing the gridded rainfall data nowadays. So that will help us to. These are the points where we need to study the climate patterns over the years. Rainfall, the same thing we have to apply for the stream, so that we can come to know how much is the stream influence of the streams. These are the, you can say, the different, you can say, data sets. So we have the, you can say, this digital elevation model, land use, land cover, soil map. So we can get from different sources. Okay, this is the, you can say, the dam digital elevation model, like how it is varying. Some of the, you can say, these are like inputs for any model, any hydrological model. They're all available now as a geospatial data sets. You can download and you can use. If you want really interested, you can prepare also. That's what is the thing you want to know. So these are the stream network, how you can prepare. This is all completely preparing from the, by using the watershed analysis in the ArcGIS or QGIS, we can completely use and we can prepare. You see, this is like administrator now. You see different directions of the streams are there. It's not a watershed. So we need to make the watershed from this one. Okay. So this is the, I can say, watersheds which really having this thing. This whole district is divided into this many watersheds. So in this one by one, we need to study now what is the, I can say, how much water is coming and how much is appearing as a flow, all the things. So this is the basin where the gauge measurement is there at the outlet. This is the place where the outlet gauge, you can say, data is there. So that is the place where we will do the measurement now. So that is the thing we use, and this is like a all calibration validation using the SWAT model, soil and water assessment tool model. So we applied here, and then we try to understand how much the, you can say, this flow, all the things takes place. We are, you can say, simulated. This is the, you can say, overall, you can say, the model, you can say, setup, and then doing the, you can say, simulations. This is the, you can say, the data is available at this is the station, and this is the sum of the, you can say, we need to know whether how much the correct what we are doing or not. These are the, so the parameters. As you see, some calibration, it comes fine, and when come to validation, it's not so good. But as like I said, like this type of things now, so it's not so easy. Like a number of years are gone increasing. It's not easy to get the, you can say, good validation values. Some of the, you can say, the simulation, you can say, the parameters which are available, which we need to, we can say, simulate, or which we need to understand. Okay, so these are all like a parameters which you are getting to during the calibration process. Okay, most of the things even you can estimate at the level of, you can say, sub-basin level, basin level, or even the stream level, like that. So that is all like a possible now by geospatial data sets in GIS. We can able to verify. So you see that dot BSN means basin level, dot RT is like a dot sol means like a soil group. So that like that we will have the different, you can say, things are there. There's what there we can change the parameters. You see the thing now. You see here there are different, you can see, units now. So where you can go and you can change the parameter, and accordingly you can get how much change you can get. That's all possible through geospatial methods. Some of the, you can say, simulations, how much simulation is coming for the calibration. So this is like a observed, and then this is the, like a simulated one, how those are there. for validation period, how the flows are there. Okay. So basically the I can say the how the I can say average monthly flows in the I can say the particular basin. So the historic and then this is like historic means whatever is the I can say IMD means the observed data will be there. So we are the I can say using the I can say observed stream flow, and then we that the same thing we are doing simulation with suppose IMD observed data, then how much will come. Then later we can do with the historic means that is climate model data. Climate model data how they are give. Those all things we can check. Same thing with the future also. You see here some of the things which you can see here now like it is appearing like a future 2006 to 2040, 2041, 2070 like that. We can make like next 100 years. This is like a above is stream flow and below is this one. So I don't know whether it is clear visible for you or not, but everything will give you the different picture. So in the future really the climate the stream flow is going to, you can say how much next 40 years 30 years it is like a division like a thing. So how really this much you can say how much you can say the change is there in the future. That all things which you can see here. Okay, so here this is the I can say different. We can say the points and then where we can simulate the things. So here this is the I can say the what is the historic thing and what is the I can say what is the I can say beginning of the century, mid-century and end century, how the each of these rainfalls are average annual rainfall, how much variation is there. You see this thing in the I can say beginning century there is going to be a reduction in the rainfall. So in the future also, that's what is the one of the observation. That's what is the thing we can get. Like by using climate model data, we can see some the reduction in the rainfall. Some even we can get some even the I can say improvement also depending upon the area, depending upon things we can get. Okay. So once again, this is like a monthly, like each or 12 months of time. So each of the I can say models in the future like how they really changes. Okay, so stream flow, suppose different we can say things scenarios like you see the most of the future things are like a reducing in the stream flows on a monthly basis. That's all like a thing observation here. So here different we can say scenarios like historic you see from 1970. This is like historic stream flow conditions. Okay, so this is when compared to the I can see here there is like a reduction here, of course some reduction in the value. So in the beginning of the century you see there is a reduction in the things 70. So of course later after this one is like improving the I can say the things. So it's not so like when compared to the century, then after 40 then the improvement in the I can say availability of the rainfall further also. But these are all like a climate models. Now you can't take like a 100% reliability. Like we have to say with a so what is the reliability of these things. For that we need not to one climate model. We have to do the number of climate models. In our case study at the time we used only one climate model. These are some of the you can see the once again the monthly stream flow things variations here. So whatever is the historic and future. So every you can say the 10 years of the things how the things are you can say changing. So most of the things is like it is like a reducing in this is the zone like reductions in the you can see monthly flows which are available or shift in the flows. Two things are we can take as a climate change, whether reduction or shift in the availability of the flows. Okay, so this is once again a 10 year you can say change. What is the Kharif season? So Rabi season, summer, how much is the you can say stream flow variation? And when compared to the you can say historic, how much change? This all will tell us figure that whether that really changing or not. So can we see some of the negative means? Of course, the change is like is decreasing. Yeah. So here most of our we can say things which we are explaining right now, they are all available as a now we can say explain right now. They are all available as a paper. So any of you interested, you can always check these things which are right now as the climate change right now explaining. This is the paper already and previously watershed models. Okay, so this is the you can say real time model we are trying. So these are all like things available. So any of you are interested now, so these things all we can download and we can see the papers and then we can get those things. So what I want to say one thing here, so you can really get the whatever the development which is coming in the geospatial techniques. Okay, presently, so the trend is like you can get a huge data sets in the QGIS or ArcGIS. You can use high resolution data sets and high temporal resolution, means almost like you can get a daily data sets. They're all like will help you to understand the better way the hydrological process or simulate the hydrological process or even forecasting. So like just somebody saying like a floods. So we can do the floods. Now the improvement in all these techniques really will improve your understanding, like how we can able to forecast the floods. That's one of the main important thing. So can you forecast like a 5 days before, 1 day before, some hours before, all things we can really influence by all our geospatial data. So geospatial data really will change your way of understanding your overall, you can say this hydrological process. So this I want to conclude my talk actually. So and open for the discussion.
Okay, now it is time for question and answer. Participants, please ask if you have any questions.
Hello.
Hello.
Yes, sir. Venkat Reddy, sir. It's a very good presentation actually, but you have covered wide range of geospatial methods and other things. I have two queries, sir. Actually, that whatever you have mentioned, all these geospatial methods. In the geospatial methods, your SWAT also is one tool, right? You're saying that
One
SWAT
of the
is like
it's a hydrological model actually.
so it's a hydrological model in the sense it's like a ready-made, readily available tool to use that software or.
Yeah, it's a readily available tool. It is software. It's a one hydrological model software actually. It's available. So the input all we can is available as a plugin to either QGIS or ArcGIS.
Okay.
You can add that as a plugin.
Okay. Whatever you have shown, all the results and other things, all these things used. I mean, all these results have come through SWAT model, or are there any other geospatial tools?
Yeah, some things I told now, like something there is no SWAT model, like something like we said geotagging those things and something initially I showed. We developed all, I can say my own, you can say the part of our research work. Those things are developed like what is you saw in the initial event based model. SWAT is the other model which is like a climate change things.
Yeah, but your model shows somewhere that you talked about the finite element modeling and other things, and you have shown your partial differential equations also. How these equations, been developed further for any kind of new basins? Is that something like are we going to change these equations based on the boundary conditions of the various basins, or is it like a constant model for all the basins? How those equations are going to change for other basins if you consider?
Yeah. So here it is very important thing actually. So here the basic equation they are called actually the Saint-Venant equations, and they're also called actually physically based equations. And once they are the basic equations, and once you can reduce them as a kinematic wave equation. That's what is the things we use in the model development. So they will not change from basin to basin, but the parameters which you are going to give as input to those things they will change from basin to basin. Suppose I am using for the Maharashtra one basin now, I am using for the, I can suppose in Telangana one basin, the input parameters for those things may change, like a Manning reference. Those things will change. Okay, so that will change, but you said like a boundary condition, like what is the boundary conditions we are keeping. Those things may change, but the basic equations, the finite element method, like whatever we made actually, finite elements, those things, how much element you are preparing, what is the size, those things will change. Accordingly, input parameters will change, but not the basic modeling methodology. That will not change.
So that means that your SWAT model or any other particular tool having particular equation inbuilt inside, or do we have any flexibility to change the equations as per our convenience based on our previous research equations or any kind of models?
Yeah. So now that yes, sir, that flexibility is nowadays I said like it's like a more it's a possible actually in the even QGIS or ArcGIS or even in the now presently available you can say programming methods na. So you can either like they suppose SWAT you take na, that is like inbuilt equations will be there. They are developed on those things how the process are simulated. So some other things some are developed. Suppose you want to make your own thing, so you start you can say from the scratch and you prepare the your own you can say process building, then write the program, like nowadays Python tools are available, C++ tools are available, those things, and give all the inputs from geospatial tools, geospatial data. Suppose all the boundary point data, all you can provide, that will take your equation and then it will simulate. That's possible now.
That means that still we need to use mathematical models, to solve the equations and to form the global matrices for the finite element, processes, right? Still, all those
Yes.
things are still that we need to do, or any softwares that we can use.
For you are saying like
I mean, because solving those big equations is very difficult. Actually, we need to use mathematical solutions, and there are many mathematical solutions that we have, as we studied earlier in our school day, college days. So, all those things are still that we need to carry out, or are there any softwares are available by eliminating all these analysis and solving equations?
This is also very important nowadays now. So like, there are so many tools are available. You see, one thing you may heard, some of you may be heard who are hearing. So there's something called R programming language, R programming. So most of the things are inbuilt things are there, and even some MATLAB tools are available. So for you, no need to make a start like a matrix solver is there. You don't need to try like a writing inverse matrix those things. You make a formulation of your things and then make that one. That is automatically inbuilt program. We can say tools will take they will take care.
Okay, sir, if you don't mind, can you go back to your slide number 37?
Slide number 37. Yeah. Yeah.
Sir, here these results are arrived from SWAT model or any other tool?
No, it is not SWAT. That's what I'm saying. This is like a developer, my own model actually. This is like a from the basic fundamental equations taken from the literature. So we developed the, I can say, thing actually. So autological model.
Okay, sir, fine. In this like volume of runoff, if you see that observed values and simulated values, I see that simulated values are very less than than observed values. When we see here, that means that observed values almost, I feel it is almost correct. But are there any corrections are required for this simulation or anything? Because
that's
what all the weight is very
thing.
less.
So actually here, you see some of the simulation. This is you see now here area under the curve. If you see this event, the blue color one is the you can see simulated one, and then black one is the observed one. So the area under the curve you take now. So this is like there is like you see the value will change drastically. So what may be the reason means the water you see this water is available for the you can say the basin. It is coming as an outflow. But when the model when we are making that is all going as infiltration. So we need to change some parameters in the infiltration so that it will reduce that infiltration so that it will available as a volume as a runoff.
So, sir,
so we can change the parameters. Means what is the thing is whatever we got at the time that is like as it is presented. So it is even in the you can see even as in like a publications also to say that this is the what is exactly coming from the model what we can say made, but it has to be do that corrections for the you can see some of the process.
So still there are some improvements required for the current model then.
Yes, that's the thing. You see, when come to the, you can see some of the peaks. You see, most of the times peaks are matching. Means the peak, you can say value whatever is there, it is matching. Means what is going is in between the things is the main thing is like whatever is the amount of runoff is coming is appearing in the observed, but it is not appearing in the simulated. Means there's more some water is going as infiltration.
Okay.
That's the thing. Like that.
So slide number 52, sir. Yeah, here you're saying the time is 10 minutes, 30 minutes, and 60 minutes, 100 minutes. Is this for any particular written period, sir, or is it something that you say the critical storm periods?
This is not return period. It is like a 10 minutes means is event. I said like in the event. Suppose I am rainfall stream is some rainfall is starting event. At 10-minute time, what is the situation in the watershed? That's what is the thing.
That means like at a time, this model runs only for the one particular written period, right? So
no, it is written for every you can say 30 minutes, 30 seconds it will run. And I am only put the outputs at 10 minutes, 30 minutes how it will. You see whatever this 10 minutes time come now, like I put for only for the visualization purpose these things. Even you can every minute also like a 1, 2, 3, 4 minutes. We can able to see the things and then we can able to keep one by one. We can even see like a simulation also.
Okay, so based on this model, sir, can we arrive that what is the critical storm and what is the return period based on this modeling? Because for that particular basin, if I want to take it further in our analysis, is it something that we can pick out from your results that this is the critical storm duration for a certain return period? Is that something that results are available for these basins or what? How actually?
So yeah, we did in the point of actually here, not the I can say return period type of thing. It's a critical like we want to see how the when the I can say really the flood is coming, when the I can say overall volume. It is like a completely simulation like a water is you can say what you call routing to the outlet of the watersheds on time when the time of the flood is coming. That's the thing we taken. Not like a return period. Like a return period means like every you can say maybe like the same like this line of stream at every you can say 5 years or how it is coming. That's why we didn't take actually. We can be seen actually. That's the thing. So we can take the critical storms and we can study like a suppose 5-year return period type of storm, how that is really behaving in the overall area. That may help you to for a particular you can say return period storm how it is behaving in the watershed. That we can
So what
study.
is the data set for that, sir, in your model? Data set, is that something that you can get from any remote sensing or ISRO, whether we can get that kind of, various return periods and rainfall intensities? Are there any data sets available or do we need to develop that?
Yeah. One option is data sets nowadays. They're all available in the means we need to analyze these return periods. But rainfall, observed rainfall, all records are available nowadays. IMD is providing grid rainfall data for daily basis, and even the local government. Now every government they have the even for hourly basis. Also they are providing nowadays the rainfall data sets.
So that means that it's a raw data that again we need to analyze for our particular
Yeah,
return
return
period.
periods. Yes, definitely our water resource. We have to do that calculation. Even area,
Okay.
depending upon the area, we need to calculate. Yes.
Okay. Thank you, sir. Yeah.
Yeah. Thank you.
Any other questions, please?
Yeah, actually, when you are showing this SWOT model simulated result, one thing from the previous discussion only, I'm putting this question. It seems to be a case where the process simulation is coming out correct, because the time to peak is there is little variation between the observed and the simulated thing on the last column. Whereas the volume calculation, there seems to be a lot of deviation. What may be the reason for this, sir?
Can you repeat me?
Yeah, the volume in terms of runoff, total runoff, or the volume of water at different points, there seems to be a lot of deviation from the observed and the simulated figures. Whereas the time to peak on the last column on your slide number 37, there the deviation seems not to be very high. It's almost kind of matching. So what I have got a feeling is that SWOT model or your model that you have developed, it is very much correctly simulating the process, but somehow it is not reflecting the calculation of the final variable, the output variable. The quantum is not getting captured correctly, but the process is getting captured correctly. Is it like that? What may be the reason for it?
Yes. That's what is the thing actually. So there is a, you said now, okay, there is a critical things. What I want to tell you here, there are some critical things are there. Still, that hydrological process is like very complex thing. It's a real time happening now. So it's not so easy for us to bring everything into the model and then they are event based things. Event based means like everything happen in 1 hour or 2 hours. But we need to bring every aspect of that thing and to bring here. That's like a thing, and that also like a complete watershed is not in our control. Like where the infiltration basically more takes place, where all things we need to have a check actually. That's the thing. That will make a difference.
Okay. Thank you so much, sir. Thank you.
Yeah, somebody is asking question like a Sravani, like can we obtain a gradient image from a composite image, red, green, bands, sentinel instead of them? So Miss question, can I understand this one? What exactly this mean actually?
Sir?
Dem is actually different. Actually, sentinel data, whatever you are getting, I can say that is like a that will basically reflect the reflectance characteristics. That will give the land use land cover information. Basically, that sentinel data with the red, green, and NIR bands. Dem is different. That is like we are getting the elevation there.
Can we obtain slopes, gradient image from the composite RG NAR bands?
Can we obtain a gradient? Means you mean a slope of an area?
Yes, sir. Yes, sir.
No, that's what I'm saying. That is entirely different. So from dem you will get slope, but you can't get the I can say slope from the this composite image that are pulse color composite. That is entirely different. So that is like
Digital number.
that is a reflected information, reflected data of the you can say the surface which you are obtaining at the satellite. That will give a land use land cover information. Like what type of vegetation is there, that type of information it will give.
Digital number represents the just we need to convert from DN to reflectance and then we have to use that. So
Yeah.
Digital
Dem is
number.
different. That dem will give the contour value, like elevation value. This composite image, whatever the reflectance it will give, that is useful for finding out the what is the vegetation there. Land use land cover there, vegetation or whatever it, that you will get. Surface
Okay,
features.
Okay, sir. What is the
They
digital
are very
number?
different things.
Digital number. What does it represent? Digital number of that red, green, NAR bands DN value before processing, before pre-processing.
You mean what is the digital number representing? That's what you are asking question.
Yes, sir. Yes, sir.
Yeah. The digital number is nothing but the that is a reflectance. A reflectance. Like suppose if you take the red for a particular area, how much is the I can say the in the particular red band? What is the reflectance energy there? That will receive at the satellite. That is the digital number. So that reflectance, there is like that is wavelength. That energy. They are dividing into numbers, digital numbers from the you can say 0 to 255 level. Each band, suppose for example, you have one area, there is a vegetation is there, high reflectance is there. That number you may get like a more number, like a big number. You may get like something called 150 like that. Okay. So something like a water bodies means there is a lot of absorption there, no reflectance. You may get like a values like a 1, 2 or 0, something like that. That is those values. The digital number represent the reflectance value. Surface reflectance for each band. So DEM is an entirely different process. So DEM means you need to use the photogrammetry concepts.
Okay, sir. Thank you.
Already I shared the PPT with Professor Srinivas. So
Yeah.
Srinivas will I think he will share to you also.
Yeah,
So my other things and the papers, everything is there. Your letter also really something is useful for you. You can use, and later also any doubts, anything is there. Really we can say help you.
So I think there is no questions from participants, so we can close this session now. Thank you, Dr. Venkat Reddy, for your nice lecture. Thank you very much.
Yeah, thank you, Professor Srinivasu, for giving this opportunity and then to share the what are things we are doing with all our this number of delegates through this program.
Thank you, sir.
Thank you.
So, dear participants, tomorrow we will, I think, we'll start our session tomorrow. First session at 10 o'clock sharp. Okay, we will. So we'll drop the call now. Okay. Thank you, sir. Thank you, Venkat.
Thank you, Srinivasu.
Right, sir.
Thank you all.